Calculating the mass and energy needed to make the universe function reveals a massive accounting problem. Physics cannot locate 95% of the universe. The most glaring symptom of this missing mass happens right on the fringes of observable galaxies. Based on the visible stars and gas, the outer edges of these galaxies are spinning so fast they should physically tear themselves apart. To explain why galaxies stay intact, the Standard Model assumes they are wrapped in a dark matter halo, a massive cloud acting as gravitational glue. The issue is that these hypothetical particles evade all direct detection. Because we can't observe them, their mass and distribution have to be constantly adjusted in the equations to make the math match what our telescopes actually see. Perhaps the missing mass is a symptom of a misaligned assumption about the physical nature of empty space itself. Newtonian physics breaks down at a specific point. Moving away from a galaxy center, acceleration drops predictably until reaching a mathematical threshold, A0. Here, the curve abruptly flattens. The Standard Model fills this anomalous gap with dark matter to keep gravity functioning. The Integrated Toroidal-Syntropic Model, or ITSM, identifies the A0 boundary as a hard geometric limit, a physical phase shift in the vacuum environment itself. The ITSM argues that the vacuum of space is not a void. Instead, it acts as a superfluid plenum, a quantized, actively flowing fluid environment operating on a macroscopic scale. Think of a speedboat cutting across a lake. Dense, high-acceleration objects, like the planets in our solar system, possess enough kinetic energy to slice smoothly through this cosmic fluid. In this high-energy regime, standard Newtonian and relativistic gravity function perfectly. The fluid is sheared cleanly, leaving the surrounding environment undisturbed and unnoticed. Empty space only feels empty when an object has the kinetic energy to glide through it seamlessly. But that dynamic changes at the extreme outer edges of a galaxy, where the acceleration drops below that critical A0 threshold. Out here, the baryonic mass loses the energy required to shear the vacuum. Instead of slicing through the fluid, the mass catches and locks to the inherent spin of the plenum. Just like a slow-moving barge dragging the surrounding water with it, the rotating galaxy generates a massive, physical, macroscopic acoustic wake. This fluidic friction creates a torsional drag. When we point our telescopes at these galaxies, the extra gravitational pull we measure is the mechanical resistance of this wake. The stationary cloud of invisible particles astronomers have been hunting for is actually the active fluidic wake of the galaxy displacing the vacuum. Rigid relativistic field equations translate these fluid dynamics into specific numbers. The framework derives rotational velocities from geometry, removing the need to tune arbitrary variables. This chart shows the model's baryonic Tully-Fisher relation. The solid red diagonal line is the model's geometric prediction, bisecting over 3,000 raw data points across 175 different galaxies from the SPARC database. The framework also matches the wider universe. This chart shows the effective Hubble parameter evolution. The solid blue line traces the ITSM's native volumetric decay, matching the latest measurements from the DESI collaboration. Replacing invisible particles with fluid geometry satisfies both the rotational mechanics of individual galaxies and the expansion data of the deep cosmos. This fluid structure provides the scaffolding required for mature galaxies to assemble rapidly. These systems coalesce along pre-existing currents in the plenum, which explains the mature structures currently being documented by the James Webb Space Telescope. The expansion of the toroidal manifold acts as a continuous intake, an open thermodynamic circuit called syntropy. This ordered intake of information balances local energy decay, maintaining the universe's complex structure. We exist inside an active, flowing ocean, sustained by the very expansion of space. Seeing the wake of that flow reveals a universe far more alive than we imagined.